everyone. Welcome to my talk. Again, thanks again for staying this late. Last talk of the conference. As Kyle mentioned, so I'm Alexis-Maurer Fortin. I'm from Montreal, Quebec, Canada. We're part of Boost Security, which is a Canadian-based application security startup, and we build application security posture management. And I'm part of the security research team researching on software supply chain threats. So we start with a hot take, actually, which is that the 2025's build pipelines look like the average 2005 PHP web app in terms of secure coding. This is a quote, actually, from my colleague, security research team, François Proux. So what do we mean by that? Is that right now it's a real dumpster fire, actually, the build pipelines. In my case, so like we mentioned 2005, okay, I'm a late bloomer, so at 11 years old, I wasn't really too much into PHP web apps back then. I was more into playing video games. So since then, but I've learned about all the horror stories back then and the lessons learned as well. So I learned about these. So web app security has improved drastically over the past 2 decades, and my IT skills as well. But the build pipelines, they really lag far behind. So let's clarify what we mean by build pipelines. So the modern world depends on software. We all know that. Developers, they write code, they mix in open source code. Everything is packaged and shipped by CI/CD. CI/CD runs with high privileges, which means it has access to secrets like tokens, signing keys, but it's also the bastard child, often neglected by dev teams and security teams alike. Up until very recently, actually, most pen testers actually didn't care about and look at those systems, but now they do, and because they're really, really juicy targets. The other thing is that even if CI/CD itself is hardened, by the very nature of it, it needs to have access to privileged systems to actually bring your code into production. So by the very nature of it, it's a highly dangerous target. So much so, especially in the open source world. So much so that we came up with the idea me and my colleague François, is that we should probably rename CI/CD RC as a service, because it's really what it is, actually, because they're systems that are highly privileged, like I said, waiting to receive triggers over the network to process data and execute code before uploading the results somewhere else. And that data includes, like, for example, pull request metadata, branch names, code itself. And so to make it clearer, let's fix the slide, actually. Yes, RC as a service, that's much better. So in the recent years, actually, there was a couple of, well, just in recent months, actually, there was more and more open source build pipelines that have been targeted. So in March of this year, you probably heard about the very popular GitHub action that got hacked, TG Actions change files. In this case, the attackers compromised the transitive dependency of TG Actions change files, which allowed them to insert malware into it and have access to secrets. The initial compromise was of the review dog action setup action. They managed to get credentials, a personal access token of a contributor of that project. But then once they had access to that, they managed to backdoor it, and through transitive dependencies actually managed to compromise the TG Actions change files action. So just like other researchers came to the same conclusion, we came to the conclusion as well that the intended target, this was a targeted attack as well. The intended target was Coinbase, actually. But unfortunately for the attackers, they got caught really, really close to their intended target. But once they got caught, instead of just, not doing anything, they decided to just go and nuclear just go nuclear, which essentially what they did is that they replaced their malware payload with a simple memory dump snippet, which essentially in the end, it dumped all the secrets in plain text in the workflow run logs for anyone to grab in the end. So everyone running the compromised version had their secrets dumped in plain sight, especially open source projects. So that was the end result of that. So we had personal access token, NPM credentials, PyPy tokens everywhere. And one that's More recent, actually just in August, was when the vulnerable GitHub action in the NX repository. NX is there's a multiple NPM packages that are built through this repository. So there was a vulnerable GitHub action in that repository that was exploited, and the NPM publishing token was stolen. So the malicious versions of multiple of those NX packages were then uploaded. They contained a post-install script malware, and the malware stole environment variables, NPM credentials, GitHub credentials, sensitive data, OpenAI API keys. In the end, it exposed the data publicly on the victim's GitHub, so it actually weaponized the credentials they had stolen on the machine to actually expose the data stolen on a repo on the profile of the users. So around 1,700 users had secrets leaked like that. And then in a subsequent phase, the attacker used the GitHub tokens retrieved to change the visibility of private repos to public ones. And in the end, there was 6,700 repos that became public, which shouldn't have been. This one is really interesting. So my talk is not on AI, but I'm going to mention AI a bit in the talk. So in this case, which is really interesting, is that AI was used by the victim to unintentionally create the vulnerability itself that got exploited. And also, the attackers then used AI in their malware to actually steal stuff from the victim's machines. So in detail, it's an AI coding agent that was involved in the introduction of the vulnerable GitHub action workflow that was exploited, which in this case, it's Cloud Code. And by the way, this is public. Everybody can go and see the pull request that did that. That's why we know it was Cloud Code, because it's the co-author of the actual commit. And then the malware itself leveraged local AI CLIs like Claude, Gemini, and Q to actually identify the sensitive data to steal. What's interesting is maybe you've heard as well another attack that came a little bit later called Shayolud, which is actually what is being thought is that the threat actors are actually the same ones that did the NX singularity compromise. And they actually use some credentials, GitHub credentials, from this attack to actually do their next one. All right. So let's stop for a moment and picture where the build pipeline sits within the software supply chain. So here, there's an amazing framework called Salsa, which is supply chain levels for software artifacts. It's a really great framework. Some people heard about it before here, I guess? No?
This is Texas, so
yeah,
everyone's heard of Salsa.
Oh, Salsa, of course, yeah. But this type of Salsa. Okay, a little bit, okay. So originally from Google, then now it's under the Open Source Security Foundation. Essentially, it maps out the supply chain and the threats of each step of the supply chain. So I'm going to go in a little bit more detail what these mean a little bit. So on the left-hand side, we have the producer, which is essentially the developer writing code, typically on their laptop, using Git to commit and push code to a shared repository. Most often GitHub. I'm going to talk a lot about GitHub today. They open pull requests, which often automatically triggers the build step. So that could be GitHub Actions, Circle CI, Jenkins. And the artifact produced by the CI will often be uploaded to a registry so that other people can consume it. In the case of open source software, it could be packaged on NPM, PyPy, Docker, Helm, Terraform as well. But as Kyle was mentioning, in Texas, you know, this is more the type of salsa that you're familiar with. So we're actually going to turn up the spiciness of the salsa here and focus on the build step, which is what our talk is going to focus on today. So so there's a bunch of threats that apply specifically to the build step, which what I'm going to focus on. And you have to consider it because it's a really critical part of the software supply chain. The build step has direct and transitive dependencies that might be vulnerable to the list of threats that you can find here. This diagram is an earlier version of Salsa. Actually, Salsa has is being updated more and more and has a lot more detail and expands on those threats I'm going to be talking about in the build pipeline. And also, let's not forget that the build step is actually RC as a service. So now I'm going to describe the types of vulnerability we can find in the build pipeline. So the first one, what we call is a PON request. That is when an attacker PR means pull request, just to be sure, contains files that modify the behavior of tools already present, leading to remote code execution. So the usage of those tools is why we came up with the name living of the pipeline. So the attack, I'm going to explain more in detail later. So the attacker is essentially using risky features of existing tools present in the build pipeline. The second type is called template injection. Template injection, so these are mustache expressions, just like you have an example there on the slide, that are used to do command and script injection, depending on the context where the expression is actually interpolated. The third one is what we call bot-mediated confused deputy, which is a fancy way to say that if a pipeline trusts a non-human identity, for example, dependabot, to run high privilege actions, we can actually bypass the authorization logic and confuse the bot to do what we want, essentially. And finally, we have, spoiler here. Finally, we have self-hosted runners that are not ephemeral. So let's recall earlier that we renamed CI/CD RC as a service. So what we mean in a runner in a build pipeline is essentially a full VM that is spun up for the given job that we give it to run our whatever we want for it. For example, running tests or linters, compile, etc. And by default, these what we call hosted runners, which is essentially the VMs that are provided by the platform. For example, GitHub Actions. They could actually be, you can provide as well your own runners, which is called self-hosted runners. And one of the big risks of doing that is actually having non-ephemeral self-hosted runners, which means it's not created and destroyed for every run, so it can be reused between runs. Of course, when if those can get compromised by an attacker, it means that they're able to then, since they are not destroyed, they can be reused for persistence. And they have the possibility to poison other jobs that might be run on them and access their secrets that could be present in memory. And of course, if it's running in your infrastructure and you can have persistence on that system, you can actually pivot and target other systems in your environment. So let's walk through a typical attack of this. In this case, it's going to be an example of a pull request. So here we have an open source project hosted on GitHub in a public repo. It uses GitHub Actions to build, package, and distributes its signed artifacts. It has a GitHub Action workflow that triggers on a risky event, which is called pull request target. I'm going to talk a lot about this type of event because the big thing is that it exposes secrets from a PR, a pull request you make on a repo coming from a fork. So if you open a pull request from a fork of a repository, you still get access to those secrets in your build pipeline. And you're going to see why this is really important. So in the end, the goal of the attacker here is to get the secrets and be able to compromise the build artifacts of the repository and the pipeline. So to reach this goal, the workflow needs to have RC vulnerability and an interesting secret. So the remote code execution allows the attacker to dump the memory of the runner, which contains the interesting secrets. The reason that a remote code execution allows the attacker to dump the memory is, again, that those VMs grants sudo to the Unix user of that job. The reason is, again, we give the most permissions because developers, they just want to do everything they want and not be blocked when they want to do that. And often these types of exploits, they can be completely stealthy, zero-click. As I have demos later, you're going to see why. So this was just a little example of the much larger GitHub Actions attack tree that we've built at Boost. As you can see here, you can have, in this space of the tree, this is where you have arbitrary code execution in the pipeline, and you get all the way to compromise some downstream components. There's many ways to reach that, and many ways to actually to prevent this from happening, as you can see. So this looks more like a subway map than anything else. So lots of things you can do. So what does an actual vulnerable workflow look like? So we're going to look at one together. So here you have, this one is running on a risky trigger, heal pull request target. So because it lacks a branch filter, the workflow could be exploited from pull requests to main or other branches containing this pull request, workflow. And also, it does not explicitly define the permissions for the GitHub token. So it's the default read and write permissions. In GitHub Actions, the GitHub token is a credential given to the workflow every time it runs. So it can do actions. It has permissions with it and call the GitHub API, for example, to read the content of the repo it's running in or modify things as well. So by default, it's given read and write permissions. The next thing is that it's running in an unpinned container. So it's pulling an unpinned container for running. So in this case, since it's not pinned, the dependency can change beneath our feeds. And the next thing is that it checks out untrusted code from a fork. And then after that, it references overly privileged personal access token in the right here. Actually, in this use case here, it's saying that it gives write permissions to the whole GitHub organization. And again, because it's in a pull request target, like I mentioned, this is exposed to pull requests from a fork. And then the next thing is that at the last line is we have make running there, and it allows us, because make, you can control in the pull request the content on the file of the make file. You can actually have remote code execution thanks to that. And finally, the last expression here, we actually have Git branch name injection here. So by putting this payload in the branch name on GitHub, we actually get injection. So this example was on GitHub Actions. So does this only happen on GitHub? Absolutely not. All modern CI platforms that trigger on events from a control system, source control system like GitHub are vulnerable. So GitLab, Circle CI, Azure DevOps, OpenShift Pipeline as Code, Jenkins, they all trigger when opening a pull request. And depending on the configuration, of course, may expose secrets to that pull request coming from an external untrusted pull request. Even in the context of building code from a fork, like I mentioned. So basically, it depends for each platform. The devil is in the detail, but the same concept apply across the board. So I mentioned this earlier, living off the pipeline, what we call LOTP. So let's keep in mind that on platforms like GitHub Actions, an external contributor cannot directly modify the workflow file in their pull request and execute it with privileges. So you cannot have an external pull request from a fork that modifies the workflow, the pipeline itself, and it executes the changes you do there. So you have to, it's a fundamental security boundary. So the attack surface isn't the workflow itself. It's the tools that the legitimate workflow already executes. So you have to abuse the environment, essentially. Living off the land, this is where it comes from. Same thing, but here adapted to pipelines. So most commonly, you drop a malicious config file for a tool like a linter, compiler, test tool, and more. And usually, we're just abusing what is expected functionality for all these tools. So we actually built and boost Living Off the Pipeline catalog, which you can find at this address. I forgot to put the QR code, but the slides will be available after the talk. In this catalog, right now, we have 48 tools already that are fully documented with POC payloads, and we have up to 31 more tools that are waiting for full write-ups. And the latest tools we're bringing in are all the coding agents and the CLIs, which are really interesting tools to abuse as well. So we're going to have a look at two types of LOTP exploitation. So first one is through config files. So the first one on the left is mkdocs, which is a static site generator. So what it allows is that you can specify hooks in the YAML that point to actually arbitrary Python that get executed when it renders the static site. So since it's arbitrary Python, we can essentially run anything we want here in the actual Python. So very useful, very useful. Then the next one on the right, which is really funny, is actually Trivy. So Trivy is a security scanner actually that you can actually abuse. But the thing is, since the template for the output, it uses the Go template syntax, you have a limited form of RCE. It's not the same thing as executing full arbitrary Python like the other tool. So you can actually still extract environment variables and do DNS-based exfiltration through abusing the template engine. So the next examples are tar and of course bash. These tools, they may not have a config file, but will behave differently based on environment variables. Obviously, since we cannot change the environment variables directly, these usually don't get abused directly, but we can still use them as second-order remote code execution. So we've seen real-world scenarios where we actually poisoning bash was really useful for us. All right, so I'm going to switch to a demo now. So I'm going to be using our own Messy Poutine CTF. We actually built CTF on GitHub for demoing and exploiting these types of vulnerabilities. So I'm going to be showing the TTPs step by step. So I'm going to be showing on the left, I'm going to have the victim organization. On the right, it's going to be the attacker's organization. In this case, it's me in both cases. But there's going to be, we're going to start with a trivial injection and progressively climb up to more advanced TTPs. So of course, let's keep in mind that what I'm going to show is actually baby steps, and the simplest scenarios, but they're still very, very common actually. So, all right. So I'm gonna mirror my screen. Okay. All right. Okay. So on the left here, we have the actual repository with the vulnerable challenges. So we're going to start with a really, really simple example here. Level 0. So the first job actually triggers, we can see here on the GitHub event when an issue is created. It's not really, it's a bit better. Yeah, okay. So it triggers on when an issue is created. It references here a secret, which is the flag we want to get. And you can see in the payload here, it's actually checking for profanities in the issue body. And the interesting part here is that, as you can see here, it's expanding the GitHub issue body in the bash command to actually find those profanities. So I have a setup here on the right where we have the webhook website, where I'm going to be using that to actually send my payload, the actual secret. So I'm going to copy my payload here. We're going to go. So we're going to go in the repo, just simply create a new issue. And then we just copy our payload. And then we create the issue. And then what we're going to go and see is that we created our issue. We go in the actions of the repo, and you can see that the actual action itself, so the fries job is actually running. All right, let's go see our webhook website, and here we go. We just received the first secret in the content right there. So now we're going to move on to the next job, which is very similar. In this case, it's running when we add a comment to an issue. And contrary to before, we had an injection in bash. In this case, GitHub Actions are built using JavaScript, and you can actually use the official GitHub Actions GitHub script to put any JavaScript in there. And we actually have same thing here. We are using the body of the comment, and we actually have a JavaScript injection in that case. So I'm going to copy the payload. Whoop. And we're going to comment on that. So we can see that we are triggered on the issue comment, on the cheddar. Job is running. By the way, I'm going to explain why we have like fries, cheddar, gravy, toppings, and stuff. Why? Yeah. Oop.
Well, you will have to explain why it's not cheese curds. It's cheddar.
Yeah. Of course, when I do my demo, it doesn't work. I probably copy-pasted the payload in the wrong way. Usually just a little space and it will mess up your payload. Yeah, I think so, yeah. Here we go. And yeah, here we go. We got the flag. All right, now we're going to move on to a more advanced example. Now we're going to target the gravy step. So as you can see, this time is running on the infamous pull request target I was mentioning earlier. And we can see that it is referencing a secret. We don't have any injections here, but one interesting thing is that it's running npm. And npm, it's doing npm install, run lint, and npm start. And npm, you can modify the behavior using the package JSON. So what we're going to do here is a little different. So already on the right, I already forked the repository from. So I'm in my fork here. So since npm, like I said, is a LOTP tool, so we're going to abuse that. So I'm going to go and modify the package JSON. And we're going to modify. We could have done it with the lint job or start, but in the case we're going to do it with the start. And hopefully I copy my payload correctly this time. But we're essentially just going to replace the npm start command. So I got my Lascon branch. So now, like as I said, I modified it in my repository, which is a fork of the repository. Now I'm going to open a PR from my repositories branch on the actual Gravy overflow repository. As you can see, the base repository is the Messi Poutine one from my repo. Now, to be stealthy, I'm going to open it in draft pull request so I don't warn anyone. All right, so I open my PR. And we're yeah, exactly. Actually, I forgot something. It has a check for the name of the PR. Just need to add the gravy word in. That's why it didn't trigger. That's just a CTF thing we did. Actually, I'm going to have to close and reopen. Will it trigger? Yes, here we go.
So in this example exploit, everything you're doing is mimicking what a malicious person would be doing within their own fork, everything they've got control over, and without anybody on the actual project side having any ability to stop or intercept, you're actually exhibiting an exploit.
Yeah, exactly. And I think, I think I cleared I received the payload, but I cleared it. So I'm gonna re-trigger it. Yeah, I'm gonna close that. Yeah, I'm gonna recreate it. Here you go. Okay, now it's queued. That's running. Setting up Node, downloading the internet, npm install. And here we go. I received the secret. So like we were mentioning, that's the thing, is now you didn't receive any notifications that I opened my PR on your repo, and I just ran your pipeline, and now I'm doing it manually, but this can be automated, and then it opens, closes, and then everything's running, and you didn't notice anything. So now I'm gonna show you a third one, but I forgot to open the video. This one, because of it involves using Dependabot. So I'm going to be showing it through here on a video, because sometimes when we open with Dependabot, what happens is that it takes too much time for it to get on. So this type is going to be what I called confused deputy earlier. So you're going to see in the workflow here, we're moving to a more advanced level. It's essentially it's going to be the same kind of workflow as we just did with the pull request, except the big difference is that this workflow, it's again running pull request target, and then the job is pretty similar, using the same job here. But the big thing is the line here, where we actually check for the actor to be Dependabot. So we're kind of blocked right now because I cannot be the author Dependabot, but we can actually, there's a trick actually to trick Dependabot for doing that. So yeah. So now we go, the first thing we do is that we go in the fork, and we're going to enable Dependabot on our fork, because by default it's not enabled by default. So we're going to enable that, and then That's why we did a video, because this can take like forever before it indexes the project and then actually goes and creates the pull request to fix and update your dependencies. So this is what we're going to abuse here from our fork. So you note that Dependabot actually, like I said, opens a PR towards your fork. It creates a branch, creates a commit to actually update your dependencies. So we're going to open a PR from that branch from our fork in our fork towards the Messi Poutine actual repo. This is the first step. But when we're going to open the pull request, it's not going to execute our workflow because the author of the pull request will be me, in this case, the attacker. But then we're going to abuse Dependabot functionality to actually do that. All right, so we've opened a pull request in draft mode again, so we don't warn you that we're doing that. And once that's open, you can see that the workflow did not trigger, because the author, again, is the attacker. All right. All right, so as you can see, so now what we're doing is that now we're going to go and put our payload, like we did earlier in the package JSON, on our main branch in our fork. This is really important. So we're going to do that, just like before, just like the previous attack. With our webhook, really important. So we commit to our main branch of our fork. All right. Now remember, we have the Dependabot pull request on our repo that is in that specific Dependabot branch towards the main branch of our forked repo. But we also have this same branch. We have a pull request from that branch towards the main repo as well at the same time. But now we modified the main branch of our fork. So now we have to tell Dependabot, hey, I modified my main branch. Please rebase on that branch, essentially, because there are changes you don't have. So we're going to ask it to do recreate. Now it's going to rebase and force push into the branch. But what that's going to do is that it's going to mean that the author of the commit will be Dependabot in that branch. But remember, that branch has a PR open on the main repository as well at the same time. So now, because you're looking at the actor in the workflow, the workflow in the main repo is going to be triggered, because now it's going to see that the actor is Dependabot. So we're essentially impersonating Dependabot in doing executing our payload. So now Dependabot force pushed, and as you can see, it got triggered, and you can see that the author now is Dependabot, and it ran the actual workflow, and we have the secret. As simple as that. All right. So that was the demo. Now I'm going to go back and do this. By the way, if you don't know, I like motorcycles, if you don't know this. All right.
I may be getting ahead of you here, and that obviously looks scary as a series of things you can do, but how much have you seen that this is real world available?
Oh, you're going to see nice slides that show you nice stats about that are really, really scary and should keep you up at night. Yeah, my pleasure. We're here to spread the good news and everything. All right, so but we're nice. You saw how we can exploit those vulnerabilities, but the follow-up question is how can you defend against those? So that's what we're gonna cover as well before I show you the nightmare stats. So the main things you can do actually to protect yourself is going to be threat modeling your first of all your SDLC with Salsa. The next thing will be to inventory and reduce the amount of dependencies that your build pipelines have. But I mean specifically your build pipelines. I'm not talking about your software packages and stuff, really specifically your build pipelines. Apply the least privilege in those pipelines. Configure branch protection on your repos. And of course, run static code analysis on your build pipelines to find those injection vulnerabilities we saw earlier. And also consider using runtime protection. So there are, of course, the slides are going to be available after that. But essentially, the first these are GitHub organization specific settings you want to select. First thing is going to be to only allow the actions you want to run in your organization, not allow anything your developers want to run, ideally. Then you can disable repositories that want to use self-hosted runners. Ideally, you just don't use them at all. And if repositories require them, then you specify them to use that. You can set default permissions to your workflows, or the GitHub token I was talking earlier. You can select across the organization and put them to have the default permission of read-only. Of course, if it's not possible and you get pushback on that, you're also going to need to specify them directly in the workflows, like I'm going to show you. There's a nice little checkbox here that says allow GitHub Actions to create and approve pull requests. That's disabled by default. Never enable that, please. That's not good. And you also have the this is especially true for the open source projects. So make sure you require approval to run workflows on pull requests from forks for all external contributors. So essentially, one mitigation for the attacks I showed earlier is that you can mitigate by not allowing first-time contributors to actually execute the workflows directly. You need to approve that they are run in their PRs. Sometimes it's tough or less manageable for open source project. You can limit it to first-time contributors. So as I was mentioning, you need to explicitly set the permissions on the GitHub token. By default, ideally, no permissions at all. And then you can start this way and then only add the actual permissions you need for the job. One important thing when you resolve secrets in your workflows, this is how you need to resolve it. If you do it dynamically this way, this is going to load actually the whole secrets objects in memory. So if you do that in your workflow, and I can execute anything I want in your workflow, then I can just dump the memory and I will have the whole repository and organization secrets that this workflow can have access. So this is really dangerous. Of course, use environment secrets. Only PRs that are targeting specific environments are allowed to run these workflows. You can configure the environment to be protected and require approval before the workflow runs. So essentially, you isolate your production system credentials from the actual pipeline running. Next one is avoid using long-lived credentials in your workflows. Ideally, use OpenID Connect for that to replace those long-lived credentials. Carefully review the permissions given to that you give to your identities using OIDC, because it's actually pretty easy to, for example, give read-write access to your whole AWS account by mistake to your pipeline. So OIDC is good, but be careful of what you're giving as permission. Let's be aware of, as I mentioned, risky workflow events. For example, pull request target that we exploited, workflow run, issue comment. When possible, use the pull request one. The reason is that the pull request doesn't present your secrets to PRs from a forked repository. If you must use risky events, of course, statically review the workflows for injection and pound request. Avoid interpolation in script context, bash, and JavaScript, like we saw earlier. Instead, always interpolate in an environment variable or action parameter. and also to limit the impact of LOTP tools. Avoid doing a git checkout in the current working directory of your repo. Check out in a subpath, and also be aware and review what kind of tools are available in your pipeline. As mentioned earlier, just avoid self-hosted runners as much as possible. That's the easiest solution, especially in public repos. And of course, if you really have to use them, make sure they don't run privilege things in there. You try to limit what they're doing as much as possible, because again, if they're not ephemeral, then you're just giving easy access to your infrastructure. And finally, there is solutions like Step Security Ardent Runner that can be used to detect and respond to actual pipeline exploitations. So they audit the behavior of the pipeline during execution, like outbound network connection, file operation, process execution, and you can even block and filter to only allow domains, so you wouldn't allow for example, my nice website I was using for my exploitation. All right, so now, and you also have Poutine. So Poutine, or Poutine, like you say in English, but it's Poutine, the right name. So this is, Poutine is our open source SaaS scanner, built specifically to actually scan pipelines to find those injection vulnerabilities, dependabot, confusion, all those things that I presented. So Poutine is actually, it's the name of the Canadian dish from Quebec, actually. And what's funny, why we use the name of that dish, which the gravy and the fries, that's the reason for the names of the workflows earlier. More specifically is that Poutine in French actually means messy. So that's why we used it, because it really represents well like how build pipelines are right now, which is pretty messy. It's really easy to use. You can point it to your GitHub or GitLab organization. It will efficiently discover and scan all your workflows across your organization. Under the hood, we use Rego. We expose a DSL, so it's really easy for people to actually extend the rules, create more. And as I mentioned earlier, we also have what we call remote tail branches, what we call I talked about earlier. If you have a workflow that's also not just in your main branch, but other branches, I can still open pull requests to that workflow and exploit it like I did earlier. So we have a feature to actually find those, what we call stale workflows that are still lurking in your repos. Yeah. So now I said I wouldn't talk about AI much, but recently we actually added the Poutine MCP server. So it allows you to two things, actually automate the feature to scan your environment. But the main thing that's really useful is actually we have a tool in the MCP server that will inline correct your LLM actually when it generates workflows, for example, for GitHub Actions, which for the NX maintainers would have been really useful, because it wouldn't have made them introduce a vulnerable workflow in their repository. And as you can see, it's pretty easy to add. You update the latest version and you add it to your tools. So this one I'm going to go quickly over it. This was like for extra. The main stuff has been covered. I'm going to just talk quickly about we've been working on is actually analyzing at scale these types of vulnerabilities. So we've essentially taken our Poutine scanner, created more specific and targeted rules. We built a back-end system around it to actually scan at scale multiple repositories and projects. And we have like 200,000 GitHub repos that we've analyzed. We've responsibly disclosed vulnerabilities we found on multiple organizations that are listed there, little names. And this is the interesting part. So out of 200,000 repos, 440,000 workflows, we found around 200,000 findings, which are what you would find with Poutine open source rules. But we have, out of those, these are our custom rules where we call them high confidence findings. So we have around 10,000, but out of still 10,000 is still pretty significant. Out of those 10,000, like I said, those are really exploitable findings, so that you can, most of the time are 0-click, just like I did in my demo. And out of those, 70% are actually true positive. So we actually triage them and actually disclose. And we have about 28% false positive, and then around 2% where you need a little bit more conditions to actually exploit, but it's still a significant number of them are actual 0 days in pipelines that we have to disclose to people.
So is that 6,500, 7,000 true positive vulnerable workflows or vulnerable repos?
Workflows, yeah. So you can have like hundreds of workflows in a single repo, yeah. So it kind of, this is quick, like since we index and we transitively deep dive into the dependencies of the build pipelines, it kind of gives a nice graph like that, so we can actually find which repositories or entities, what we call like organization, can be exploited by one of their transitive build dependencies in their pipeline. So this, and also the other way around, like which organizations can be targeted with a single vulnerability. So, this is the best thing for attackers is finding 0 days in transitive build dependencies. So, yeah. So I'm going to go quickly over this one, but in the last year, we were finding vulnerabilities statically, like I was mentioning, and then we decided to try to find if we could find the exploitation of those vulnerabilities live. So we built something like this, a backend to actually do this as well. So we actually consume public events on GitHub to actually analyze live if we can find actual attacks being done. So as you can see, this is a funnel. So we go from about 5.5 million events, and all the way down we do analysis on our backend live. It's about 5 minutes behind, and we get about 46 actual true exploitations per day. So, all right, I was a bit over time, but all right. So thank you for coming for the talk. You can find more information on these things on our blog at Boost Security. You can also use our tools and projects like Poutine and the Messy Poutine CTF, and the Living of the Pipeline catalog, and a little shout out to a couple of other researchers in that space. So it's a global effort. So thank you. So I'm gonna check with the conference how. Yeah. Right. So
Where to find the slides?
Yeah.
So far, it's mostly been from the presenter.
The presenter, okay.
But if you send us the slides, we will attach them to the video.
Oh, perfect. I'll do that. Yeah. Okay, that's how it's going.
Yeah. So we'll have the videos on. The videos should be up. I'm not sure what the time frame is, but they should be up on the LastCon website soon.
Awesome. Is there any other questions? I'm here to respond. Yeah.
I'm not sure how to phrase this coherently, but it sounds like there's just maybe some bad architectural designs and things like GitHub workflows,
Yes.
GitHub Actions.
Yes, correct.
Has there been any proposal of like how to correct that or a better way to do it?
Yeah. The big thing is the legacy, like all the pipelines that are actually running, and not GitHub. You know, they would have to break a lot of stuff. There have been improvements that have been coming, but it's because of it's going to break a lot of stuff. So
they close the vulnerabilities, they just break a whole bunch of existing workloads.
yeah, exactly. Yeah. Yeah.
It also doesn't help that the GitHub Actions documentation is a total labyrinth.
Yeah, it is. Yeah. There's a.
I hate GitHub Actions so much just because they're just so bad at writing documentation.
Yeah.
And then the other thing that came to mind is it seems like a lot of what's happening is secrets are being extracted from what is perceived to be a protected environment from an attacker's control. But it reminded me of in if you remember how we invented address space layout randomization,
Yeah.
where we had a virtual address that then got translated by something trusted to a real address. Has there been any talk in the research space of maybe coming up with something like a token, like, I don't know, it sounds weird, but a token to actually represent a valid GitHub token, and then some sort of proxy where it gets translated to and done on the behalf of like a temporary container, so that if anything inside the container is exposed, they are ephemerally generated secrets,
Yeah.
And are of no value as soon as that.
Yeah, well, some of the solutions I presented where you use OIDC for your, not a long-lived credential for your, representing the access of your pipeline is one of those solutions. Maybe not as good as that, but also the environment secrets where you actually segregate the deployment of the execution of actually putting uploading your NPM package to NPM, for example, where you actually separate that from the actual building. So you actually upload for example, your one workflow builds the artifact, and then another one, which requires approval and cannot be triggered by an external person, using environments like I showed. That's where it can be used. But yeah, I get where you're going with that.
That's a really big one. But
Yeah.
are there other things? I feel like there's other sensitive tokens and stuff like that that would also need to be used, but maybe if it could be done safely through a broker,
Yeah.
or something.
Yeah, but usually OIDC is the main thing you can use for that, because you actually have the identity of your workflow and you know exactly where it comes from, and that's when you can actually leverage that information to give only the specific access that your workflow should have in your system, ideally. But yeah, with NPM stuff, it's actually GitHub and NPM have been working on improving those tokens, and because the issue is that they are long-lived in that case. So